So welcome back, dear students, in the course of Strength of Material. Today we will discuss torsion in shaft and we will derive the torsion equation. And before going to the subject, let's introduce myself. Myself, Dr. Irshad Ahmed Khan, Associate Professor, working in Department of Mechanical Engineering, Sagar Institute of Research and Technology, Bhopal. So this is the assumptions before deriving the torsion equations, and these assumptions are material is homogeneous isotropic, material is not sorry, soft is not initially distorted. So these are two assumptions, and third assumptions is the displacement at any point is proportional to the distance from the center of the shaft. I will explain later on more. So that means the shear strain at any point is proportional to distance from the center of the shaft, and that cross section or the cross section perpendicular to the axis of shaft before and after of twisting, and the angular twist is uniformly along the length of the shaft, and the shear stress developed that should be proportional to shear stress. That is meaning. So all what I've explained, these point number 3 and 4, let understand with this diagram. So the 4 ones say that this cross section is perpendicular to the axis of the shaft before and after applying the angle of twist. So you can see this part, this should be the proportional. So this is initial if this radius and this, so this is there is a this plane must be perpendicular on the axis of the shaft. So another thing, understand that this is shaft. You can see the length which having length L, radius R. If you subject torque clockwise direction at the right side, and suppose this side is a fixed one, so what happened actually? So that element OA, it's it turn by angle theta and reach new position, that is OA dash, and along the length it is also make an angle phi, and that phi is very small. So you already know, and I already explained that uh, this it will be a shear strain in the shaft, that is phi, and it is equal to a dash upon the length of the shaft. So this is called the shear strain. So that the you can find the shear strain from this formula. And to understand that point third, which I told you in the assumptions. So if the another element, that is OB, it is below the A, and if you are after the application of twisting moment, so it is reached to B to B dash, and so it's making a different angle here, that is phi r at a distance r, small r, from the center of the shaft. So this phi r is a strain on this element OB. Okay. So similarly, we can calculate the strain for this element. So we can conclude that the shear strain is proportional to the distance from the center of the shaft. Okay, hope you are understood what assumptions I explained you before, and with this example. So this is diagram you keep in your mind, and let's move to the next slide to understand that more concept about that, and also derive the equation of torsion of the shaft. So let's see. So this is angle of theta is that theta is angle of twist. Already you know that. At the radius is small shaft, BB dash as r theta. Simple, we know that. And the shear strain at radius r, that is phi r. So we can BB dash L and replace this BB by r theta by L. Similarly, shear strain at phi in at radius capital R, you can say. So this would be A dash r theta, and we can write phi is equal to similarly like this. So A dash upon L r theta upon L. Simply, वैसे ही है. You can understand. Okay. So we know that this formula maximum strain phi is equal to tau upon G, where G is the modulus of rigidity, and and that tau is maximum shear stress at the radius r. So what happened? Shear strain phi r at this radius small r. Okay, so we can write the shear strain at the radius r upon G is the shear modulus or modulus of rigidity. Both are the same thing, and the shear strain at a radius r theta by L. We have already get in the previous slide. So what happened? You just equate both, so we can get so tau r upon r g theta by L, and similarly for the at radius r we can write tau r upon g theta by L. So both side this term g theta by L are common, so we can write tau upon capital R and tau r upon r equal to g theta upon L. This is one part what we have get till now. So let's understand the second part. So you can see this diagram. So we are consider a elementary ring at radius r of thickness dr. So what we are going to be, so this elementary ring. So first we will get the area of this ring. So area of the ring will be 2 pi r dr, and stress at shear stress at the radius r, that is tau r, we already know, and tau is the maximum shear stress at capital R. We already explained it that. So what will be tau R in term of tau? So it can be R small r upon capital R, small r upon capital R into tau. This is a simple, because both are the proportional, so we can write like this. The shear force on this small ring, small area, so that is 2 pi r dr into tau r. Then put the value of tau in tau r, this one here, so it's become 2 pi r dr, and this, so we can write tau r 2 pi r square dr. So this is the shear force on this small area, and if you know the shear force, so we can calculate the twisting moment of the ring while taking the moment about the center of this shaft. So twisting moment about the center of the shaft, I already told you that that is del T del F into R. That put the value of del F here, and R, that become tau R 2 pi R cube into dr. Then total twisting moment on that total twisting moment on the shaft. So we can calculate capital T and this integrate from 0 to R. So after the calculation, it's look like this, and where this term pi by 2 R, that is called the polar moment of inertia. Polar moment of inertia, and you already know the polar moment of inertia is pi upon 32, okay, and d की power 4. I think you know that. I explained in the previous class. So how it is, and so 32 into, it is, if put 2r, so it's become 16 r की power 4. Okay, hope you understood. You just put 2r in place of d, so it becomes 16r. So it's cut इसको आप you can cut, so it's become pi by 2 r की power 4. Okay, so this is called the polar moment of inertia, and represented by the j. So this term become tj equal to tau into r. In the previous equation, what we all know that tau r is equal to g theta by L. So just equate that value. So we can we can we can get this relation tau. So T upon J equal to tau or G theta by L, and this equation is called the torsion equation, and this is very important equation to get the different value on the shaft if it's subjected to torque D. torque T, and the many other parameter of shaft can be calculated by using this equation. Hope you are understood this torsion equation, how to derive it, and it will definitely help you to solve the coming coming numericals on problem on the shaft. So thank you so much for listening this